Okay, you guys. Yeah. Okay, you guys have your homework out. We have a question on number 51. Any questions before we get to 51? We're going to La Center today for golf match. Yeah, exciting stuff. Right to 51. Good with that? Okay. Girls? Okay, 51. In how many ways is it possible to arrange the two numbers A and B in an ordered pair? Okay. So an ordered pair is a number and then another number, right? So, yes. Yeah, I'll go back to that as soon as I'm done with this one. So, how many different numbers could I put in the first spot if I'm choosing between the numbers A and B? What? 2 of them. I could choose either A or B, right? And then how many numbers could I put in the second spot? 1, I guess, because I've already chosen A or B as the first one. So if I multiply those together, how many different ways are there? What? 2. Okay. So why is it called an ordered pair? Yes? Because the order they're in matters. Yeah, because there's 2 different ways. I don't know. Yeah, I don't know. That seems like kind of a strange question, but I guess that's what they're trying to get at. Does that kind of help, Noel?
Yes, I just didn't like understand the
Yeah.
ordered pair part.
Oh, okay.
That kind of ordered pair.
Okay, so we're good? Okay. Okay, and then did you say number 48? No, Kindle? Okay. You and your friends are picking up videos at a video store. You've selected 7 videos, but you only have time to watch 3 videos together. How many different ways can you select the 3 videos to watch? So, time out. The first question is a bit of an opinion question, but it says, does the order in which the videos are selected make a difference? Probably not, because you're just going to watch 3 movies. So we're going to go with a combination because the order doesn't matter. But you could conceive of a situation where the order would matter, right? But we're just going to say it doesn't matter, and so that's our clue that it's going to be a combination. How many videos do we have to choose from? 7. How many are we selecting? Okay, so I'm trying to figure out what 7C3 is, all right? Now, I know that this is something that you can do on your calculator, but I'm just going to emphasize the formula because I can. If we use the formula, it would be the first number factorial divided by, what's the number that goes here? Right, 3 factorial because it's this number right here that comes next, times what? Does anybody remember? Right, 7 minus 3 factorial, which is 4 factorial. So it would really be 7 factorial divided by 3 factorial times 4 factorial, all right? And Josie has given us the answer already from her calculator, but I'm just going to keep going with this because I can. How did we get 4? Nope. How did we get 4?
3. 7 minus 3.
Okay, it's not a race. I don't know why you and Jordan are so... Okay. You just... Okay, yes. 7 minus 3, Josie, is where the 4 comes from. Okay, the fun thing about doing factorials when you're dividing is what can I do before I do all this crazy multiplication? Yeah, I can do a ton of canceling. 4 and the 4, 3 and the 3, 2 and the 2, 1 and the 1. And then I can also cancel out 3 times 2 is 6, right? And so 7 times 5 divided by 1 is 35. Is that what you said the calculator got you? Yeah. It says what? 35. Okay. All right. Any other questions from the assignment? No. Jamie, did you get what the assignment was? Okay. So were you able to do it and no big deal? Okay. All right. Will you pass those forward, please? All right. So what we're doing today is we're just building on the idea from yesterday. Yesterday we were just figuring out the different ways how to count the number of things that the number of ways that something can happen. Today we're going to use that to figure out the probability of something happening, right? And the reason why they're related is because in order to figure out the probability of something happening, you have to know the number of ways it can happen in the first place. Okay? All right, not loving that, so let's just skip that and get right to the good stuff. So here's the formula for the experimental probability of an event. And so experimental probability is a little bit different from theoretical probability. Theoretical is what are the odds of it happening in theory. So like if I'm flipping a coin and I'm keeping track of the number of times that tails comes up, in theory, if I flip a coin 50 times, how many times will it come up tails? I'm just asking a question. What? 25. In theory, it would be 50-50, so it would be 25 out of 50. However, in reality, if I were to flip a coin 50 times, it's not always going to come up tails exactly 25 times. So the experimental probability is the number of times the event happens divided by the number of trials. So for example, that would be the number of times that we got tails divided by the number of times that we flipped the coin. Okay? So experimental probability is a little bit different from theoretical probability, which I guess we will talk about tomorrow. Moving on. All right, so easy stuff. You're going to love it. Of the 60 vehicles in a teacher's parking lot today, 15 are pickup trucks. What is the experimental probability that a vehicle in the lot is a pickup truck? In other words, if you closed your eyes and randomly threw a baseball up in the air, what is the probability that the windshield that would be broken is a pickup truck? Right, 1/4, because 15 out of 60 are pickup trucks, and Jordan correctly reduced that to be 1/4, okay? You can write this, if you would like, as 25%, but most of the time, probability answers are left as fractions, okay? Do not leave those as unreduced fractions. So reduce the fractions if you can. No, I'll give you credit either way, but I'm just saying that usually you're going to see the answer as a fraction, 1/4, okay? All right. A softball player got a hit in 20 of her last 50 times at bat. What is the experimental probability that she will get a hit in her next at bat? 2/5, because she got 20 hits out of her last 50. That reduces to 2/5, or you can write that as 40%. Okay, super easy.
What we're doing.
Seems unlikely, doesn't it? Doesn't it always get more and more difficult? Okay, sometimes actual trials are difficult or unreasonable to conduct. In these situations, you can estimate the experimental probability of an event by using a simulation. A simulation is a model of the event. So for example, we could simulate the flipping of a coin on a calculator by saying, if I want to know how many times I get heads out of 50 flips, do you want heads to be the number 1 or the number 2?
1.
Number 1. Okay, so then I can go to my calculator and I can go back to this probability menu and I can have it generate some random numbers, okay? So I want the lower number to be 1, I want the upper number to be 2, and I want to do this 50 times, okay? So this is me running a simulation of flipping a coin 50 times. We decided getting heads was which number? 1. Okay, so if I push enter, 50 numbers come up, and then I would go through and I would count the number of times that a 1 came up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, so in our simulation there, we got heads 22 out of 50 times. Okay, what Josie said is 100% correct. It was probably going to be 25, but probably doesn't mean always. Okay, All right, so let's say on a multiple choice test, each item has 4 choices, but only one choice is correct. How could we simulate guessing the answers? Right, we know you got a 1 out of 4 chance of guessing correctly. So based on what I just did on my calculator, how would we change that to be a 4-problem multiple choice test? How would we change that instead of being a heads and tails situation to be a multiple choice test with 4 answers? What? Right, okay, so I would change this so that instead of just generating numbers from 1 to 2, I would generate numbers from 1 to 4. Okay, so again, I'm going to go math, and then I'm going to go over to probability, and I'm going to choose this number 5 random integer. Some of you go straight to the screen that I just showed. Some of your calculators have this system right here. So I want the lower one to be 1, the upper one to be 4. How many numbers should I generate? I don't want to do 1,000. I'll show you in a second. You want to go 10? Okay, so we're going to simulate this 10 times. You guys that have the other calculators will just get this right here. So it says random integer. So the first number that you type is the lowest number you want. Then you go comma. Comma has its own button right here above the 7. And then you type what you want the highest number to be. And then you go 10 times or whatever we want to do. Okay? Then we need to decide, though, which number represents us guessing correctly. And it could be any one of them because they all have the same chance of coming up. You want to be just, okay, I was going to say 1 because it's easy, but let's just be weird and go 3. Okay, so in this, I'll do it again. In this simulation, how many problems did I get right? We decided the answer was 3. Okay, so 1, 2, 3, 4. All right, so I'm going to write that down. So that time I got 4 of them correct. Right. Right, that's a good point. So you're going to get different answers than other people on some of these questions. But for right now, let's just do this all together, okay? Now I'm going to hit enter again. So it's going to simulate it again. How many times did I guess correctly this time? 3 times. Then I'm going to do it again. How many times did I get it correct this time? Once. Then I am going to do it again. How many did I get right this time? None. Okay. How many did I get right the next time? 4. Then I'm going to do this, let's see, 1, 2, 3, 4, let's do it 5 more times. How many did I get right that time? 5. Okay, nice job, me. And then if I do it again, I got that right. Oh, 5. I'm getting to be a better guesser. Let's do this 3 more times. 2 that time. So I'm starting to get tired at the end of the test. I'm not guessing well anymore. 1. And then the last time I will run this simulation. This time I get it right 3 times. Okay. So this is us running the simulation of guessing on the multiple choice test. I could have passed out 10 different questions to each one of you and had you guys guess the answer and then gone through and seen how many times you got them correct. But that would have taken a really long time. So the calculator is easier. Now I can answer the question, what is the probability that you will pass the test by guessing at least 6 out of the 10 answers correctly? Right, 0. That never happened in our simulation, okay? Is it theoretically possible?
Yes.
Yes, but according to this, it never happened, okay? Now what Jordan said is right. If I did this as a homework problem, she might have generated 10 numbers and gotten it to happen like 6 times, right? Okay, so you might end up with different answers to this based on the experiment. What's that? If I would have gotten a 3 6 times, then that would have been, I would have said 1 out of 10, okay? But I never got a 3 6 times, so I never passed that multiple choice test, okay? Then I would have passed it 1 time out of the 10 times that I took it, all right? Okay, what's the probability of passing if I only have to get 50% or better? No. What's the probability? Right. According to my simulation, that happened 2 times out of the 10 times that I did it. So that's 2 out of 10 or 20%. Okay? And again, if you guys all did this on your own, because I never got a 6 threes, yeah.
You never got 6.
I never guessed correctly 6 out of the 10 times. Okay? The set of all possible outcomes to an experiment or activity is a sample space. So we've talked about 3 different things here, so let's list those sample spaces so that we know what that is. What is the sample space for flipping a coin? But no, what is heads or tails? Okay. Whoops, tails. Okay. What's the sample space for guessing on a multiple choice test? A, B, and C, and D, I guess. Okay. Then you'd have to list those all out. So those are the sample spaces for those things there. All right. If each thing in the sample space has an equal chance of occurring, then these are called equally likely outcomes. Are these equally likely outcomes? Yes. If you're purely guessing on a multiple choice test, are those equally likely outcomes? If you're purely guessing, yes. If you're just like, I used to, when I was in high school, we had clocks that had a second hand on there, and if I didn't know the answer, I would look up at the second hand, and if it was between 0 and 15, I guessed A. Between 15 and 30 seconds, I guessed B. 30 and 45, I guessed C. No, it's random. It got me to where I am today, this high-paying, highly, prominent job. So it must have worked out for me in the end. Can you guys think of a situation where they are not equally likely outcomes?
Oh yeah. If they have if it's a pizza and the sizes are not equal.
Okay. So if you are cutting up a pizza and the slices are unequal, and you're going to grab a random piece of pizza, then you're more likely to get maybe a bigger one or a smaller one. That's a little bit of a stretch. Anybody else think of something that's random but not equally likely?
Picking a shirt in the morning if you shut your eyes.
Playing at a casino. Good. That's a good one. That is not random because they have the machine set to do certain things more often than others. Okay? Okay. So now we're going to talk about, I guess, in the same section, theoretical probability. Theoretical probability is the probability you're more familiar with, more comfortable with. That's the probability of something happening in theory. So again, flipping a coin, the theoretical probability of getting tails on each flip is 50%. Okay. How about rolling a 6-sided die? What is the theoretical probability of getting a 2? 1 out of 6, because there's 1, 2 out of the 6 sides. So it's the same idea, except this time we're not running experiments to figure this out. We're just using our knowledge of the world. Yeah, we're using math to figure it out. All right. So, for example, what is the theoretical probability of getting a 5 on one roll of a standard number cube? Yeah, so a die, 1 out of 6. I don't know why they call it a standard number cube. Maybe because die is an awkward sort of word. I don't know. Okay, this is a tricky one. What is the probability in theory of getting a sum of 5 on one roll of 2 dice? So to figure that out, hold on, slow down. To figure that out, we need to use what we were working on yesterday. So the first thing we need to figure out is how many different rolls can you get on 2 dice. So how many sides are on the first die? 6 times how many on the second die? 6. So that means there's a total of 36 outcomes. How many different ways can they add up to 5? Can you list them for me?
1 plus 4.
Right, 1 plus 4, 2 plus 3. That's not it, because then I can whoa. Not yelling and not interrupting. 3 plus 2 is different from 2 plus 3. That confuses students sometimes, but think about the first die as being like a red one and the second die as being a green one. A 2 on the red die and a 3 on the green die is different than a 3 on the green die and a 2 on the red one, right? So those are different outcomes. So that means I could also get a 4 plus 1, okay? Josie, you can't get a 0 because there's no zeros on any of the dice. So how many possible outcomes are there that make a 5? 4. And so that means our theoretical probability would be 4 out of 36, which reduces to 1/9. Okay? How are we doing so far? You guys are all pretty familiar with this. You've talked about this before. Okay, good deal. All right. So this is going to get us into what we were talking about yesterday. It can be easier to use combinatorics to find theoretical probability rather than listing and counting all the equally likely outcomes. So that's where we're going to get into what we did yesterday. All right. So let's make this a little bit more complicated. What is the theoretical probability of being dealt exactly 2 sevens in a 5-card hand from a 52-card deck? Okay. So the first thing we need to figure out is how many ways can we get 2 sevens? All right. And so it says there are 4 sevens in the deck, and we are trying to choose 2 of them. So that's 4C2, because the order that we get them doesn't matter. Okay? Then we have to figure out what's the number of combinations of getting 3 cards that are not sevens from the 48 cards that are left. So for that, we go 48C3. Okay? So if you multiply those two things together, that gives you the number of 5-card hands that include 2 sevens. Does that make sense? Yeah. So I did 4C2. That gives me the number of ways to get 2 out of the 4 sevens dealt to me. And then I did 48C3. That's the combinations of all the other cards. And I used 48 because I can't use sevens. All right? Then we have to divide that by the number of possible 5-card hands. So to do that, there's 52 cards in the deck, and I'm dealing 5 of them. So that works out to be 103,776 divided by about 2.6 million. So that means you have about a 4% chance of getting dealt really a pair of any numbers out of 5 cards. Does that make sense how I did that? That's a little trickier than getting a 3 on 1 die. Not easy. You haven't doing that since you've been 6 or whatever you said before. 5. Josie, you got her? Tell me when. Okay. All right, let's try another one. Okay. This says, what is the theoretical probability of being dealt all 4 sevens in a 5-card hand? So I'm going to have to go 4C4 because I want to know what's the probability of getting all 4 of the 4 sevens, okay, times how many cards are left? Yep, 48. And how many of those cards am I choosing now?
1.
Just 1 because I already have 4 sevens in my hand. And again, that's divided by 52C5, okay? So I'm going to do this in one step on the calculator. I'm going to go parentheses. 4, and then I'm going to go over to that probability menu, and I'm going to choose the third option. So I'm going to go 4C4 times, then I'm going to do what? Then I'm going to do 48, and I'm going to go back to the probability menu, and I'm going to do 48C1. So that's the number of different poker hands that have all 4 sevens in there. So there's only 48 of those, okay? And then I need to take that and divide it by the total number of hands altogether. So that's 52 C5. And that comes out to be a very, very small number. You guys know what this -5 means? It means move the decimal over 5 places to the left. So that means it's going to be 0.0001. Right, didn't I do 4 zeros? Oh, I only did 3. Okay, 0.000185. So very, very, very small chance of being dealt for sevens. Okay. All right. The last thing that we can do with this is what's called geometric probability. So this is, instead of dividing the number of ways that it can happen divided by the number total, now you're dividing the area that you want the thing to be in divided by the total area. And I know that this is just going to be like further confession that I'm a complete math nerd, but I was just thinking about this the other day, because this is sort of how you could figure out the probability of getting a hole in one. If you divide the area of the golf cup by the area of the green, because I'm not as good as Macy, okay? So when I hit a golf ball on a par 3, it's just going to land randomly, basically somewhere on the green. I'd like to think that it's more likely to land closer to the hole, but that doesn't seem to be the case, okay? So anyway, for this one, it says a batter's strike zone depends on the height and stance of the batter. What is the geometric probability that a baseball thrown at random within the batter's strike zone will be a high inside strike? So all we need to do for this is figure out what's the area of this rectangle right here, 24. And then take that and divide it by the total area of the strike zone. What? You did already? Okay, so 17 times 22 is 374. So if I divide those, what's 24 divided by 374? You got that too? 0.064. Okay, so it would be about 6.4% if all you're doing is you're throwing the ball randomly at the strike zone. Okay, and we know that when Samantha pitches, you're not throwing it randomly, right? You're aiming for a spot. Just like when I play golf, I'm aiming for a particular spot. But if we just knew it was going to be a strike in there somewhere, that would be the probability of having a high inside or strike. Okay? All right, does that all make sense? Started easy and then we kind of fell off the cliff there at the end? Yeah, that's usually how it goes. All right, so here is your assignment.